Welcome everyone to February Wales Southwest Local Network online public lecture. My name is Dr. Carleen Campbell and I'm the 2021 chair of the Wales Southwest Local Network. Tonight's webinar will be on the history of microprocessor development at Swansea University. Before I introduce the speaker, during the webinar, if you have any question or questions, please go to the Q&A section and type your question there or questions. You can express your thanks in the Q&A as well. It gives me great pleasure to introduce you all today to this online webinar. I will now take the pleasure to introduce our speaker for tonight, Dr. Tim Davis. Dr. Tim Davis graduated with BSc in Physics with Electronics from Swansea University in 1975. Following PhD studies in the Department of Electrical and Electronic Engineering at Swansea, he moved to the Southeast to work for Redifone Telecommunications. Returning to Swansea in 1980, Dr. Davis took up a post as systems engineer in the newly formed Microprocessor Center. In 1988, he moved into the Department of Electrical and Electronic Engineering as a lecturer. His lecture courses have ranged from telecoms subjects, microprocessors, and electronic circuit design. His latest innovation in teaching is a take-home laboratory for the first-year electronics students, which has enabled the whole cohort to carry out experiments on microcontrollers from the safety of their homes. Microprocessor as a subject is evolving constantly as new devices become available. Even now, plans are being made for teaching the next generation of microcontrollers. At this time, I will hand over to Dr. Tim Davis, our speaker for tonight. Thank you.
Thank you very much, Dr. Campbell. And if you'll pardon me, I'll bring up my presentation and we'll see if we can make that work. There we go. Well, thank you again, Dr. Campbell, and good evening, ladies and gentlemen. This talk is very partisan. It's very much my view of how microprocessor teaching has developed at Swansea University, because I've been there on and off quite a lot, and I've been able to witness quite a few of the developments and be instrumental in some of them. So I think the first thing I want to say is about the microprocessor itself. When did they come into existence? Well, the first microprocessors appeared towards the end of the 1960s, and they were used for niche applications such as desktop calculators, like the one I'm showing here, the Intel 4004. That's a 4-bit processor. It's designed to replace large chunks of TTL logic in desktop calculators and simplify them and make them a lot cheaper. But it wasn't really a general purpose microprocessor. Significant event, 1970, 2 new members of staff were appointed. Professor David Aspinall, who was appointed as head of department, and his colleague, Dr. Erik Dagless. Professor Aspinall had previously worked on the Atlas computer in Manchester, which was a very significant development in computing. I have here some pictures of Professor Aspinall, who I regret to say is no longer with us, and Professor Erik Dagless, who very much is. And you may notice if you can see the writing, there's he's got a certificate there for volunteer core values from the IET. And presumably that was a qualification he recently gained. 1972, a new chip is marketed by Intel, the Intel 8008. This is a proper microprocessor. This is a genuine 8-bit microprocessor. And almost immediately, one is sent to Swansea in a little cardboard box, and it's eagerly pounced upon by the two gentlemen, and they began to incorporate it into a desktop computer. And by the end of 1972, as I understand, they had a prototype of their computer, which they called Cybernaut, working. I'm very grateful to Professor Erik Dagless for sending me some photographs. And the one on the left is the prototype Cybernaut, and then the one on the right is a production model. Now, the production models were made by a company called Data Lab, as you can see there, and they also used the design for a data storage unit to be added to an ordinary oscilloscope, so you had a digital oscilloscope. Now, very briefly, I'll tell you about the controls there, because you can see that there's controls labeled address and data. Those are lever wheel switches, so you could set up an address in octal, and there's a display on the left to show both the address and the contents of that address. Why Cybernaut? Well, that stands for Coleg y Brifysgol Abertawe, which in English, of course, is University College of Swansea, which was our official title prior to the Swansea University going independent. Why naught? Well, programmers always number from 0. It's amazing how things stick in your mind. When I saw those photographs a couple of months ago, two things immediately came back to mind. One of them was the Minitron display. And the Minitron display was a dual inline device, and it had little filaments like light bulbs for the segments of the 7 segments. And you had to be very careful not to put too much current through it, or you burn a segment out. So that was used on the prototype, and I'd forgotten all about it. The other thing I'd forgotten about was these lever wheel switches, which you saw on the prototype photograph. And these are very ingenious. You pull that lever down and the numbers flick past in the window. And so you can rapidly select the right digit. The ones used in Cybernaut were locked, so they wouldn't go beyond 7 because they were working in octal. 1974, a lot of things happened in 1974. The team of David Aspinall and Erik Dagless began to give courses for local companies. And I remember that British Steel and BP Chemicals and various other firms regularly sent people around for training in microprocessors. And the course was took place over 2.5 days. And my esteemed former colleague, Jim Proudfoot, he was employed as a research assistant, and he was one of the tutors on these courses. Again, I'm very grateful to Professor Dagless for supplying this photograph. It shows a Cybernaut connected to a logic analyzer frame, a logic analyzer, which was used routinely in our digital laboratories, but it was acted as an expander for the Cybernaut, so you could do all kinds of experiments with it. 1974, again, a student called Andy Hopper graduates with a BSc in computer technology. And Professor Aspinall recommended that he go to Cambridge, or apply to Cambridge to study for PhD, or DPhil strictly. And after he graduated with his DPhil, Andy Hopper formed a company called Acorn with a group of other students. And quite apart from the BBC computer, which was one of their products, they went on to develop the ARM, the Acorn RISC machine. And that's found in every smartphone and tablet, a pivotal piece of technology in the world today. I think it's worthwhile just listing Professor Hopper's achievements. You can see there, I won't read them out, but you can see he's a very accomplished fellow. In addition to all that, of course, he was president of the IET a few years ago, and he recently delivered the Zenkovich lecture, the annual Zenkovich lecture at Swansea, and revealed that he's the only person who knows how to pronounce Zenkovich. I'm sure I didn't get it right. Towards the end of the 1970s, many manufacturers of chips were making kits like this, variously described as evaluation boards or experiment boards. And this particular one has got an 8080 on it. And immediately above the CPU, which is the white ceramic device, you can see another chip, and it's got a little tiny window. Now, the younger people will be aware of the existence of these things. These chips are memory chips, but they are programmable. But to erase them, you had to put them into an ultraviolet box, and the ultraviolet rays would cause the program to vanish, and then you could reprogram it. So not like flash memories, which you can program on the fly. You had to go take these chips and cook them for 10 minutes in the ultraviolet box, and then you could reprogram them. And there's other components there, which are almost certainly serial communications and random access memory. And you'd write your program on a piece of paper in mnemonics. You'd code it by hand into the binary, into the hexadecimal opcodes, and type them in one byte after another. And when it's in, you'd press go. And with a bit of luck, it would work. If it didn't, you would scratch your head and look at your program and see what went wrong. If you couldn't afford one of those kits, Clive Sinclair, not Sir Clive in those days, Clive Sinclair, the entrepreneur, he produced a microcomputer, and this predates the ZX81, predates the ZX80. This is a long way back, 1978. And you can see that it's got a CPU right in the middle of the board and various memories. I think it had 1/4 of a kilobyte of random access memory. And down the bottom is a calculator display, which was very tiny, and a membrane keyboard, which was absolutely murder. And I think that cost about £29.99 or something like that. And it worked okay, but it was a bit of a challenge at times to use it. 1978, BBC have got a program still called Horizon. And in 1978, they had a program called Now the Chips Are Down. If you want to see this program, you go on the BBC website, search for Now the Chips Are Down, and you'll find it straight away. It's permanently available. Very prescient program. It said, unless we pull our socks up in the UK, we're going to get left behind in this new technology. We're going to get left behind. And there were many things in that program which were well ahead of their time, well ahead of their time. And as I say, if you're interested, I advise you to go and have a look at it. And it's quite interesting. Some of the things have come true, some of them haven't, of course. You notice, by the way, in addition to the CPU, which is the chip, the big white chip on the bottom left, there's a collection of random access memories below and EEPROMs on the right-hand side. Now, the government of the day was a bit scared by this program, and they decided that they should put some money into centers of excellence. And they formed, they made money available, and universities had to bid for this money to establish a center of excellence at on their campus. Swansea entered into this bidding process and were granted quite a large chunk of money, and they established a microprocessor center, and it recruited staff, and the staff were employed from March 1980, I think. So in March here we are. I'm sorry, I forgot about this. This is a flyer that was produced in the 1982, I think, to accompany a trade show. And where is that handsome young fellow today? Dear, oh dear. On the right-hand side, there's a very significant piece of kit, which I'll talk about in 1 minute. And in front of me, there's some equipment which is nothing to do with the microprocessor center. I borrowed it from a postgraduate in order to have some window dressing. Terry, if you're watching, apologies for that. We also had it available in Welsh, as is the requirement. 1980, a large number of crates arrived at Swansea University, and when it was all set up, we had this beautiful HP 64,000 microprocessor development system. Now, this was a bit like going from a horse and cart to a Saturn V rocket. You know, previously, if your previous experience has been one of those development kits, suddenly being presented with a machine like this, which was capable of editing and compiling and testing programs, my goodness, what a step forward. It had a 10 megabyte hard disk. Yes, I said a 10 megabyte hard disk, a printer, and numerous pods for emulation. And I seem to remember it cost £37,000, which is roughly equivalent, I'd say, to £400,000 today. One terminal is still surviving. Thank you very much, Professor John Tucker. And he's got it squirreled away in his computing collection in Swansea University. I found this, a reprint from the Hewlett-Packard Journal, and it shows how the HP 64,000 console would be connected to its printer and to a disk drive via HPIB, IEEE 488 interface. And you can see that at the back of the console is a card frame which contained all the emulator boards. By the way, the large box on the floor on the right-hand side is the 10 megabyte hard disk, the 10 megabyte hard disk drive. It contained two platters, one removable and one fixed. And it sounded like an RB211 gas turbine engine when it started up. It was quite spectacular, but very fast. This is a rough idea of how the system was used. There's a faint dotted line you can see, and to the left of it is your target. To the right of it was the emulation system, which was in the card frame. And all that stuff on the right-hand side allowed you to see what was going on intimately inside a microprocessor. So when you plug this into your target system, you could exercise it, make the program run step by step, and examine the memory and examine the registers, do all kinds of things. Massive step forward to previous development kits. We supported quite a few microprocessors. There's a list there of all the microprocessors. Not all of them were supported equally. Some of them we only had assemblers, but the more popular micros, like the 68,000, that had full support, including a C compiler and the in-circuit emulating hardware. We also formed a users group for the HP 64,000, and this users group was had delegates from all over the place, from up in Scotland, Bedford College in London, Imperial College in London, some high technology firms as well, like ML Aviation. Anyway, now, in 1980, the way we taught micros in Swansea University changed. Previously, we'd been using Cybernaut equipment. From 1980, new equipment was purchased. And this consisted of some 3U racks containing an Intel 8085 microprocessor and memory and IO and all kinds of other things. And you didn't talk to it with lever wheel switches and LED displays. You talked to it with a VT52 monitor, which was another big step forward. And that equipment was used for about 10 years. And the person who set up that laboratory was my esteemed former colleague, Dr. Jim Proudfoot. Meanwhile, in the early 80s and mid 80s, a whole load of manufacturers were producing mini computers or desktop computers. And many of you will be familiar with the BBC computer, which is on the left there and connected to its little disk drives and everything. And on the right is an early model IBM PC, probably a PC XT. And a number of software writers began to produce cross compilers and cross assemblers to run on these platforms, because that was much, much cheaper than buying a HP 64000, as you can imagine. And also we needed a solution that could be put in front of every student in a laboratory. The HP 64000 with its 2 and eventually 3 stations wasn't suitable for that purpose. So we were looking for a solution towards the end of the 1980s that would allow us to have a per student terminal that was capable of running a compiler and so forth. I've tried a number of cross assemblers. These are only just 2. I tried a cross assembler called Crossware for the BBC computer, worked very well. And then later on, I tried a cross assembler called PC Bug 11, and we used that for a long time. Ran on the IBM PC, and this was a very advanced piece of software because with only a serial interface, it allowed you to edit, compile, and debug. And the only reason we stopped using it was that it ran under DOS, and it really didn't like Windows. And so I think when our computer laboratory moved into Windows, really put paid to the HC11. Here is the manual, one of the manuals that came with the kit of parts, and you can see it's titled PC Bug 11. That was the name of the piece of software that you ran on a PC. And then there's an experiment board on the right-hand side. These were not very expensive, and the one I've got, the one I still have, was given to me by a Motorola systems engineer up at East Kilbride. And when we moved over to these, we had each PC in the laboratory had PC Bug 11 running on it, and also had one of these boards alongside connected via a serial lead, and with an expander on it containing with interface to various experiments like LEDs and switches and motors and all the usual things. And that was a very useful, it was a nice processor. It had a lot of 16-bit arithmetic in it. And I'm sorry we had to discontinue that particular one. I think I can't really talk about microprocessor teaching at Swansea University without mentioning the group design exercise, which we started round about 2000. Now, this was inspired by the IEEE, yes, I said IEEE, not IET, the IEEE Schools Micromouse competition. And the Schools Micromouse competition, it ran for quite a few years, and Mr. John Jones was very instrumental in taking that out to schools and getting them to build these things. And then we'd have locally, we'd have a a trials day where all the machines were tested upstairs in one of the rooms in Fulton House. But I was inspired by this and said, well, we can do better than that. We can have a more sophisticated micromouse that uses a microcontroller at its core. So we launched this group design exercise, and we had our students working in teams of 5, typically. And the brief was to design and build a small wheeled robot. And this exercise took the whole of the second year. It was worth 20 out of 120 credits. So it was worth a lot of marks to the students. So it was worth doing well. I'd like to show you now a picture of a micromouse that was extant in 2006. Now, I'd like you to look very closely at that micromouse. You can see there's a microprocessor board on top, and look at its construction. Pieces of aluminium, which have been drilled and cut and folded, and then held together with 3mm bolts and metal spacers and all the rest of it to form a strong, rigid chassis. And then onto that chassis were put motors and batteries and the microprocessor and various sensors. And in front of that micromouse, you can actually see the infrared sensors which were used for detecting obstacles. On the left, I've got the list of tasks that they were required to perform, such as obstacle avoiding, line following, micromouse combat. It had to have a special feature, and all the documentation was put on web pages. So try and keep that picture of the 2006 micromouse in your mind. For the last 5 years, we've been going to Grugganog Hall for the assessment of micromouse. Now, Grugganog Hall is about 100 miles away, and so it was quite a major operation to get all our equipment to Grugganog Hall. Our senior technician, Mr. Moody, would get a van and load oscilloscopes, power supplies, and massive amount of stuff onto the van, and it would all be taken up the day before to Grugganog Hall, and we would set up in the music room. And then the students would arrive by coach, and they would do the final touches to their micromouse, and we would have the assessment of the line following, the assessment of the obstacle avoiding, the assessment of combat, and also there'd be presentations and things like that. And as I say, we use the music room at Grugganog Hall, which is very elegant room. You can see there's a massive pipe organ at the end there and a very nice piano. And you can see how tidy and beautifully laid out this is. And that would normally, in the summer, be ringing to the sound of choral music and things like that. Well, when our students arrived, things became a little bit more disorganized. And if you look at this picture, you can see this was in 2016. And this was the combat final, where we were setting machines against each other and having them to do with micromouse combat. And we were hoping to see them, some fatalities maybe, machines getting knocked off the table completely. And the reason I picked this particular picture, we've got millions of pictures of micromouse. I picked this one because everyone's smiling, everyone's happy. Even the losers are smiling. So, you know, it must have been a good experience for them. And I'm sorry to say we didn't run this exercise in 2020, not like this anyway. Obviously, with COVID restrictions, we couldn't go to Grugganog, and we couldn't even finish the micromice. They were never 100% completed. It's my esteemed colleague, Dr. Augustine Egwebe, and he's obviously triumphant there. And you can see a student on the left is holding a micromouse with little antennae sticking out of it. That's one of the machines that was constructed. And this is a still from a movie. You can see two micromice locked together. They are on a white rectangle on a black background. And the machines must stay within that white rectangle. They must not leave it. If they leave that white rectangle, they automatically lose a bout. However, they must also seek out the other machine and try to force it out of the arena. And there's a fairly complicated scoring process that goes with this. These two machines, as I say, were competed in 2019, the last time we ran the formal assessment. And the one on the left is quite advanced. It's got a little liquid crystal display on top, so you can see what the micromouse is doing. Don't forget, these machines are entirely autonomous. They're not remote controlled. It's not like Robot Wars or something like that. These are autonomous machines. You put them into the ring and let them go, and they have to fend for themselves. They have to find their opposition and seek it out and force it out of the ring if possible. Let's get back to microprocessor teaching. As I said, in 1980, we purchased all these Quandon kits based on the Intel 8085. In about 1992, we moved on to the HC11. And round about 2000, we started using the Motorola HCS08 GP32. And that was quite a useful micro. But again, it required a serial interface for the debugging. And when you upgrade your computer laboratory, what you find is the new machines don't have serial ports. That's something that's been abandoned. And there were other issues as well to do with running serial ports. So we had to look elsewhere. And by 2005, we were looking at Motorola Freescale HCS08 AW60. 2020, we'll talk a bit about the take-home laboratory in a minute. Here's an experiment board that we were using in the mid-1990s. This uses the Motorola HCS08 GP32 processor, which is smack in the middle there. Very useful, dual inline chip. The fact that it's dual inline means it can be plugged into a socket, and if the students break it, you can put another one in very easily. Also on that board are motor drivers and serial communications and other bits and pieces. The board on the left, the auxiliary board, contains LEDs, a D2A converter, switches, push buttons, and other bits and pieces, so that you can use it for, so that you can do some simple experiments without any additional hardware. And there are two DC motors down there as well. That microprocessor board, which we built in-house, was also used on the micromice in the early days. In fact, you may have recognized it from that earlier picture of the 2006 micromouse. By the end of the 1990s, we had made the switch over to the AW60 processor, and that particular development board was made in 2007, I noticed, so maybe my timescale is a bit adrift there. This is a much more advanced microprocessor, still 8 bits, but with a lot of I/O on it and quite a lot of memory, and of course it's flash programmed, and you can see it's attached to switches and LEDs and a little black accelerometer chip, which you just about see, and other bits and pieces. And to make it more useful, we attached it to that auxiliary board with D to A converter, motor drivers, which are tiny, tiny little things, and a pair of DC motors. We are on the aluminium base plate, we also mounted a plug-in breadboard, so you could breadboard little extra circuits, for example, an analog conditioning for the A to D converter. So that was very useful, and we're still using that board today. That's still part of our current laboratory equipment. But we did need a board as a replacement for micromouse. And we designed our own microprocessor board. That's about 75 millimeters square, And it's in the middle of it is the Motorola HCSO8 AW60 processor. And to the top left are motor interface chips. And so you can drive motors directly from this board. Loads of connectors around the outside so that you can tie in all the sensors and various other bits and pieces that you might want in your micromouse. This was very useful for projects as well. Quite apart from micromouse, it was very useful for third year and MEng projects. There's also a footprint near the top right, and that footprint is for a FTDI module, so you can have a USB interface as well. How did we program this? Well, for starters, there was a piece of software written originally, I think, by P&E, and it's called Code Warrior, very competent piece of software, and allows you to do assembly work, C compilation, and then allows you to download the program directly into the microcontroller and to put in breakpoints and to monitor memory locations. So we were getting back now to the utility we had with the Hewlett-Packard, but without the vast expense, because these microcontrollers have got a logic analyzer built in, a separate logic analyzer built in, so that that logic analyzer, you can invoke that using a special interface, and you can see what's going on. It's like having a little window on top of the microcontroller, so you can see what it's up to. And we are using those boards today. We're still using those boards today. That shows the typical arrangement. There's the microcontroller board on the left, and on the right is a interface box or programmer, and that plugs into a USB port. And you can see there's a ribbon cable connecting the programmer, the multi-link, to the target system. And once the board is programmed, of course, you can unplug that 6-way connector, and the board's on its own running its target program. A very useful arrangement. Now, 2018, jumping about a little bit, micromouse has moved on. It's been running something like 15 years. And we've gone through HC11 processors, we've gone through the GP32 processors and the early 08s, and we're now onto the AW60. And you can see on the picture on the left, there is a printed circuit board on top of that blue plastic circle. They've been NC routed, and we buy those in from a company. And the microprocessor board is sitting on top of that, and it's got wires connecting it to the DC motors, to the sensors, and various other things. Looking a bit naked and naked there, the students who built it, Team India, I for India, by the time that they finished it, they had given it a beautiful suit of clothes. You can see that it's got a red a red 3D printed base and a gray 3D printed top. And also there's a transparent lid, which has been laser cut from acrylic plastic and has also been engraved with the team's motif, which is that sort of jagged looking thing. And this machine was somewhat different from its contemporaries because instead of using infrared interface for detecting obstacles and for detecting other micromice, this used ultrasonics. This used ultrasonic modules. And it had a bit of an edge in consequence because it could see without being seen. Because if you use the infrared to spot another micromouse, you can be seen as well because you're blazing with infrared light. So that is a fairly up-to-date micromouse built in 2018. And that machine, in fact, is in our Hall of Fame. It's in a glass cabinet in our laboratory, and together with a number of other micromouse, which are of particular merit, and the students concerned are very proud of it, you can imagine. Now, 2020, 1 year ago, the writing was on the wall that we would not be able to run in-person laboratories for much longer. And I had the idea of giving the students a kit that they could take home with them. Well, that means it had to be fairly straightforward and not very expensive, because otherwise the students, it was going to cost us a fortune. And so during 2020, I proposed this to my colleagues, and our senior electronics technician, Mr. David Moody, really ran with this idea. He really ran with it. And I was envisaging a sort of a fairly low-cost approach. But Mr. Moody insisted that we house the kit in a nice box, and that each box have the name of the student laser engraved on the lid so that we knew who each box belonged to. And in addition, the students were provided with tools, a little zip-up tool case with pliers and wire cutters and a wire stripper and screwdrivers, and PPE in the form of eye protection, because if you're cutting wires, you've got to wear eye protection. This is something we insist on. And then you can see all the minor parts that were in the kit: resistors, LEDs, connecting wires, and other bits and pieces. And so by the start of the academic year in September 2020, Mr. Moody had put together, and his team had put together 100 of these modules, 100 of these kits. And some of them were given directly to students who were in Swansea studying in person. Some of them were picked up and then the students worked on them at home. And some of them were sent to far-flung places, such as Tanzania, I think one went to, and to Hong Kong. So these kits are all over the world. It's been quite an achievement, and I'm very grateful to Mr. Moody for taking on the practical aspects of putting together and distributing all these kits. Of course, the kit itself is only half the story. There are experiments on the internet so the students can read the scripts and try out the example programs and then do the exercises which they've been set. And that exercise and that whole laboratory took place during October, November, and beginning of December 2020. and it was very successful. And we had a few people having troubles, but not many, and we were able to debug the problems at a distance. But that's not maybe a way forward eventually. So, and there, I beg your pardon. This is one of the experiments. You can see the plug-in breadboard, and you can see the microcontroller module on the left, and then a load of LEDs in the middle, and some connecting wires, and a potentiometer, and a few other bits and pieces. And this was experiment number 4, which I hope to demonstrate to you after the formal presentation. And the students would build these things, and then they'd be given an example program, and then they would have to advance that program and do something cleverer with it. So that was quite a step forward, and not really expected, something we expected we'd have to do. We were very constrained, of course, by what microprocessor we could give the students. It had to be something that was supported on Windows machines, on Macintosh, and on Linux, and also something that was pretty surefire. So we ended up using the Arduino Nano, which is somewhat different from the micros we use normally, but it's programmed in C, and so it has that in common with our other kits. So that is where we find ourselves. We have a laboratory full of the AW60 kit, and we have a generation of students, first-year students, all of whom have these take-away or take-home laboratory kits. Where do we go from here? Where do we go from here? Do we improve on our 8-bit microcontrollers, use some alternatives, switch to an alternative 8-bit platform, upgrade to 32-bit, use an alternative language like Python? There's lots of possibilities, many possibilities. A few years ago, we entertained Professor Andy Hopper. He visited Swansea, and when he saw what we were doing with microprocessors, straight away asked, why aren't you using ARM? And that was a difficult question for me. But at the time, I said, oh, it's too complicated for the students. That is not true. So we may go to 32 bits. We may use a variant of the Raspberry Pi called the Pico, which is a microcontroller based on the ARM technology, and which can run this language called Python. So the next chapter in teaching microcontrollers or microprocessors at Swansea has yet to be written. And I'm hoping to be involved in it, even at my advanced age. So I think a little vote of thanks, not a vote of thanks, a word of thanks to some of my colleagues, like Mr. Moody, the senior technician who runs our electronics laboratories at Swansea and was so instrumental in putting together the take-home laboratory. Mr. Gareth Evans was a senior technician in the VR suite and designed a lot of the more modern printed circuit boards. Professor Emeritus Erik Dagless, University of Bristol, who provided me with some background information about those early days and some photographs. Dr. Jobling and Dr. Igwebe, my esteemed colleagues, who are also involved in Micromouse. Mr. Sean Lethbridge was a postgraduate student and did a lot of debugging of the experiments that we set students for the take-home laboratory. And Mr. Tony Green, who's now retired, but he did a lot of printed circuit manufacture for us over the years. So I thank you very much for listening to me. I hope that it was informative and a bit entertaining. And I will certainly entertain questions, but I think before questions, I might just show you experiment number 4 working. So if you will indulge me while I stop PowerPoint and switch over to my visualizer, and I click on that, I stop sharing, and I will show you instead my visualizer, which I think I can do. There we go. That's experiment number 4. You can see the printed circuit board, not the plug-in breadboard, and you can see the little Arduino board there. And if I turn the potentiometer, you can see what's happening as I turn this potentiometer. The LEDs are illuminating in sequence until we get to the end. So this is a bar graph display like you might have on a recording machine, for example, showing you the signal level. And the students have to write a program to achieve that. So there we are, ladies and gentlemen, and I'm quite happy to entertain some questions and answers. And I hand you back to Dr. Campbell in order to orchestrate that.
Thank you. I'm going to be doing, thank you, Dr. Davis. I'm going to do the questions alternatively, myself and Simon. And your first question, the Q&A, is why is there a current delay in the supply chain of microprocessor?
Okay, well, I was not aware. Let me switch back to me. Hold on.
Yes, please.
There we are. That's better. I wasn't aware that there was such a problem. I wasn't aware that there was a problem with supply of microcontrollers. I suspect individual manufacturers might have problems, but I can't imagine that there's a global shortage of microcontrollers or microprocessors. So I really can't answer that question because I don't know what goes on in these companies.
Simon, you want to go ahead with the next question?
Next
Yeah,
question. Well, it's more of a comment. Laureen and Jane Mosley, into the 1890s, I taught programming, databases, compilers, OS, AI, and expert systems in the then separate computer science department. I'm still doing some machine learning at USW.
Well, I know Laurie Mosley very well indeed, Professor Mosley, and very nice to hear from him. And I distinctly remember some of the things that he got up to when he was on staff here at Swansea University. So it's very nice to hear from Professor Laurie Mosley there. Next question.
Well, there's 2 questions from Sam Mahoney. And first he said, thank you for taking the time to speak with us. I have 2 questions. Have any groups of students really shocked you with how good their micromouse was? If so, why?
Right. Well, yes. As I say, I remember back a good few years ago, a particular group produced a amazing micromouse that had all kinds of features. It had boundary alarm. It had you programmed it by just putting it down on a piece of paper with a pattern on the piece of paper, and that told it what program it had to run. And that was quite advanced. And more recently, of course, we've seen some very, very advanced 3D printing. And some students go their own way completely and build printed circuit boards which are the mechanical part. And there have been some very, very, very elegant machines constructed. But I won't say shocked. I won't say shocked, but I've been very impressed by their activity, certainly.
And his other question is, as we reach critical shrinkage in electronics, what path do you envision the progression of the microprocessor innovation taking?
Well, now we have microcontroller modules now, which work with in conjunction with a computer, a personal computer, and you can do some quite advanced things. The latest micro I'm looking at now is made by is been designed by the Raspberry Pi Foundation. It's called the Pico, and that is such a powerful little beast, and it's tiny. It's really tiny. And I've always said that in electronics we do more and more with less and less, until eventually we'll be able to do everything with nothing. But certainly I've seen microprocessor systems go from collections of boards which have shrunk down to single chips, and those single chips have become tiny little slivers of plastic. So we've seen vast steps forward. The next question?
Right, Simon.
Next question comes from Doug. He says, hand coding was demanding, but it resulted in a profound understanding of how the microprocessor worked. Have we perhaps lost some of that nuts and bolts understanding?
Okay, well, until 2020, I insisted that first years do some programming in assembly language. And then we moved them on to C programming towards the end. But until this last year now, we haven't been able to do that when we've been using the take-home laboratory. But certainly prior to COVID-19, our first year students would all do some assembly language programming at the beginning. And that is very important, because you need to know, as you say, the nuts and bolts. You need to know that you'll be putting a byte into an accumulator or a register. You're sending that byte to a memory location, which is a port, and it has an action in the outside world. It makes an LED or a relay close, something like that. I think it's very important. Yes, I do agree that that is essential. And I suspect that a future in-person laboratory will have some, we will go backwards a little bit and reintroduce a bit of assembly language programming. You've got to remember, a lot of the students who come to us now have done some serious programming in their school or previous college. And so they are not unfamiliar with high-level languages. Carry on.
Okay, before I ask the third question, there's some comments like from Steve Kaminsky. My first computer was Kim -1. In bracket, he has 6502, and my school had an Alitar 8800. And Doug says, great presentation. Thank you for jogging my memory with all those acronyms, and I thought I'd forgotten. And then now we have Lou Briner. No,
can I address that first comment, please, from Steve?
Okay.
I also had a Kim 1, and I think I know where it is. I'm sure Professor Tucker would love to get his hands on it, but I believe I've got a Kim 1 hidden away on Singleton campus somewhere. Okay. And but I don't think I've ever seen the machine you mentioned. I can't remember what it was now. Anyway, carry on, please. Carry on.
Right. So now, from Lou Brenner, now that so many companies make low-cost prototype boards, is there still a need to design and build your own custom ones?
Well, in the case of Micromouse, yes. we wanted a compact board. We wanted a compact board that had our favorite microprocessor on it, and also the motor drive chips. And so that was, I think that was quite relevant, making our own board there, because it was very closely focused on the application intended to drive a micromouse. And rather than have motor interface chips on a separate board and things like that, it means that we had a very compact solution to go into the micromouse.
Simon, go ahead.
Charles asks, given the prevalence and performance and ready available of cheap dev tools, boards, do you have any plans to move to embed ARM devices, or are there still benefits of teaching 8-bit processing in assembly rather than 32, 64-bit in C or higher?
Right. Well, that's a very good question. In fact, one of my colleagues this week said to me, oh, we mustn't leave behind the 8-bit microprocessors because that is what's used in many commercial applications. And they're very commonplace and they're very low cost. And quite often you just do not need the power that you have in an ARM, embedded ARM. And the embedded ARM, as I said, I did mention briefly this processor called the Raspberry Pi Pico, which is different from all previous Raspberry Pis, because it's not a computer. It's not a computer, and it is in fact a microcontroller. It doesn't have an operating system on it like a Raspberry Pi 4 and this kind of thing. And it's very attractive, but you can't possibly program it at assembly language. You can only program it at high level because it's a complex beast. Carry on, please.
Gerald Marsh just to know, I wish I was a student with a take-home lab. So I guess you need to send one to Gerald Marsh.
Right. Well, Mr. Marsh, if you get in contact with Mr. Moody, if you can get in contact with Mr. Moody and slip him the appropriate amount of money, maybe he'll put one together for you. But or at the very least, we could provide you with a list of parts. But I think they cost us about £30 each to put together.
Okay. And John Baker now said, why did you choose Arduino and not Pi?
Okay, when we began that exercise, when we began the take-home laboratory, the only Raspberry Pis available, as I say, were all like things like the Raspberry Pi 2 and 3 and 4 and the W0 and things like that. But those are not microcontrollers. Those are computers. They're designed to run an operating system. They're designed to run an operating system and have a display and all this kind of thing. They are a long, long way away from a microcontroller. And in fact, there are some things they just don't do very well, real-time stuff, because they've got the operating system in the way, and they are very fast, mind you. But a microcontroller is very single-minded. It's only got one or two things to do. And I personally would not use, I know people do, but I wouldn't use a standard Raspberry Pi, like a 2, 3, or 4, for instead of a microcontroller. But now they've introduced this Pico, which is a microcontroller, and it's been divorced from operating systems and this kind of thing. I would consider that. Carry on.
Simon, go ahead.
What do you consider to be the biggest leap you have witnessed? And that's from Ian.
That's a difficult one. That's very difficult. I was quite amazed when the first Raspberry Pis, the first Raspberry Pis came out, because the idea of having a complete computer almost on a single chip, almost, there are other components obviously, but to have a complete computer that you could plug into a keyboard and plug into a display and talks to the internet on its own, I think that was quite an amazing thing to see that when they came out.
from John Tucker, there are two questions. Can you describe the early industrial applications of the microprocessor center? And the next one is, were companies hungry for the new technology?
Okay, right. Well, I can tell you some of the projects we got involved with in the microprocessor center. There was a long-running project in conjunction with civil engineering and the Water Research Center, and we built a machine which would be connected to an inspection camera, which you put down water pipes or sewer pipes as well, and it would be looking at the pipe from the inside, and it would analyze using Fourier analysis. It would look at the pipe from the inside and determine how circular it was, and from that you could determine whether the pipe was under stress, it was being compressed, and things like that. And we used a 68,000, which is of course a 16/32-bit machine, an early 16/32 processor, and that was doing the analysis of the pictures that came from the camera. The camera was very impressive. They were in stainless steel, and they had mighty hoses attached to them. They were designed so that if they got stuck down a drain or stuck in a pipe, you could attach the other end of the cable to a JCB and haul it out presumably without too much damage to the camera. That was one long-running thing we did. We made a repertory dialer for a company called Top Draw. I don't think they exist anymore. We made equipment for 3Ms to check the quality of videotapes coming off their production line up at Gorseinon. And I could go on. There were quite a few projects we were involved with. Oh, and the mini fermenter. Yes, we produced a desktop kit to control a fermentation process. So you'd have a Perspex jar with a stirrer and heaters and feedstock, and then there was a box then with pumps and a microprocessor and various other bits, and it would maintain the environment in this pot, and it was for biotechnology experiments. Were the companies hungry for the new technology? Certainly, in the mid to late 70s, the courses that were run in the university that had been started by Professor David Aspinall and Erik Dagless were very popular, and a lot of people came to those. And those courses are still running in the 80s, but of course with new hardware, with alternative hardware, but they were still popular in the 1980s.
Go ahead, Simon.
Due to time, I think this should be our last question, but we still have about 30 other questions on the list, which we're not going to be able to get around to. I will send the question to Tim so he can get a look at them all, so that he can see some of the comments you have all made. But the last question from Anonymous: do you know why the data display of the early Swansea made computers only had 3 digits, while the address display had more? Is it due to lack of memory?
Could you repeat that, please, Simon?
Do you know why the data display of the early Swansea made computers only had 3 digits?
Right,
The
that's
address
easy.
display had many more.
Okay, the 808 processor was an 8-bit processor, and it had, I think, a 12 kilobyte addressing range. A 12 kilobyte addressing range means you have to have how many address lines? Sorry, I'm saying it had a 4K address range, I think, which means 12 address lines. The reason there was 3 digits is because it worked in octal. And the biggest number you can represent within 1 byte in octal is 255 decimal, which is 377 in octal. So you need 3 digits to represent an 8-bit number if you're working in the octal numbering system, because in decimal 255, in hexadecimal FF, and in octal 377. So you needed 3 digits to display the data field. And similarly, in order to display the 12 bits, I can't remember what the exact addressing range was, but you needed triplets of bits were represented by single octal digits. But that's why the Cybernaut had a 3-digit data display, because it was displaying in octal. The reason for using octal was, I suppose, goes back to a lot of early computing applications. And as Dr. Proudfoot would repeatedly say, if you were programming at assembly language level, the middle digit of the 3 octal digits was also the number of the register that was being addressed within the microcontroller. And if you worked in hexadecimal, of course, everything was sort of displaced one side. I've never liked octal, because when you go from 16 bits to 2 8-bit chunks, you have to alter the numbers because there's not an exact fit. But of course, with hexadecimal, there's an exact fit of bits in a 16-bit number. Carry on.
Thanks, Dr. Davis, for answering all the questions. At this time, Pete Arnold will do the vote of thanks.
Hi, everyone. Well, my name is Pete Arnold. I'm another senior lecturer at Swansea University, and it is my great pleasure and privilege to propose a vote of thanks to Dr. Timothy Davis for a fantastic talk, a trip down memory lane for me, and I think for many of tonight's audience. He somehow managed to, I don't know, evoke the physical reality of electronics. I kind of lost that. I've become a software engineer in recent years, and I seem to have lost this physicalness of this reality that I remember back from the early 80s, from when I started with my ZX81, and the idea that these days students don't cook their chips and wouldn't know about cooking their chips and wouldn't know about putting chips into DIL sockets, so that when they did cook them on board and produce some smoke out of their circuits, they could fix it. I mean, it's mad. And of course, the other thing that really rang true with the talk tonight was the fact that the toolkit and that this lab at home thing. I remember when I took a year off before I went to university, that my line manager at the time gave me a toolkit for me to do the work I was doing with microprocessors and with electronics, and I still have that kit. Well, most of it. There's a few bits I've broken. And he was, I think, probably my most inspirational teacher at the time, much better than at the university itself when I got there. So thank you, Tim, for reminding me about those. And so on behalf of the committee and the chair of the IET Wales Southwest local network, I would like to propose that we give Dr. Timothy Davis a wonderful vote of thanks for his talk. And if you could do that by putting a message in the chat or the Q&A, I would appreciate it. Thank you very much, Tim.
Thank you, Peter.
Right, big thank you all. Before we end our session, just to let you know, our next public lecture will be a joint one with BCS, the Chartered Institute of IT, on March 11, 2021. The speaker will be Chris Meadows, Director of CS Connected Limited. His lecture will be From Digits to Quantum, the Technology Behind the Clicks. Is Moore's Law coming to an end? Once the link is available, we will be advertising to all for this upcoming online lecture on March 11. So I now take this time to say thank you all. I see from wherever you are, Mark is from Cardiff. He's the only one that states where he is. I could see other participants that I know from British Columbia, Canada, Caribbean, and I see Kelvin Dunn from right here in Swansea. I don't want to leave anyone out, but I just want to say a big thank you wherever I also saw one of my students from China and from India. So COVID now allows us to connect to everyone wherever you are, which is good. And I'm sure you all really enjoy Dr. Team's lecture today. Did you have something else to say, Dr. Team? Were you going to say something?
Oh, I'm astonished at all the questions that are here. And I hope that I can have a copy of this list of questions so I can answer some of them selectively. And various people have asked me why I didn't use PIC. And because I think it's absolutely ghastly processor. And I wouldn't seem dead programming one. No. I've always favored the Motorola series.
Okay. So once again, have a good night, good day, good morning, wherever you are, everyone. And we'll see you again in March. Thank you all.